We're going to continue chapter 6. We're going to be dealing with binomial and geometric distributions today. A lot of what we're going to be doing is on the calculator, and we'll go through plenty of examples in class, but I want to make sure you get the foundation of what we're talking about. So first thing, what are the conditions for a binomial setting? You can remember a binomial setting by thinking of the abbreviation BINS. So when we're talking about a binomial distribution, the first thing that you need is you only need two options, binary, success or failure. Your variable needs to be independent, okay? And we'll talk about something called the 10% condition a little bit later, but you want to think to yourself that one event does not impact the next. And your number of trials must be fixed. So you have to have a set number of trials. And S, you have to have the same probability of success for each trial. So your probability must remain constant. When we're talking about a binomial distribution or binomial variable, what you're thinking is you're saying, okay, given a set number of trials, what is the probability of this many successes occurring? Or at least this many, or less than, or more than? So for example, say I know that the probability somebody is left-handed is 13%. A binomial probability calculation would say something like, okay, out of 20 people, what is the probability that exactly 4 of them are left-handed, or less than 3 of them, or at most 2 of them? Anything like that would represent a binomial situation. So a binomial random variable is a scenario with multiple trials, and we're counting the number of successes. Like I said, our example with our lefties, okay, what is the probability of exactly 3 or less than 2 or 4 or more? Binomial probabilities or binomial random variables is true for a discrete random variable. So when we're talking about a binomial random variable, it's defined by two things, the number of trials, which is n, and then p, which is the probability of success. You'll also sometimes see x or k involved, which represent the number of successes. The most common mistake when we're dealing with a binomial probability problem is recognizing that the scenario represents a binomial situation. So you want to think to yourself when you're asked a probability question to determine if it's binomial, that you have a set number of trials and you're looking for the number of successes in those trials. So let's take a look at this example, and we'll go through this actual example here. Bill makes 80% of his free throws. He shoots 5 free throws, and we will assume each shot is independent. Let x equal the number of free throws made. Verify that it's a binomial setting. So B, there are two outcomes, success versus failure, in this case, a make or a miss. I, independence. It is stated that each shot is independent. If it didn't state that, you might argue that it's not independent because maybe he'll go on a hot streak and then the probability of the next shot being made is more than the previous one. But it does state that the shots are independent here. N, we have a set number of trials, N, that is 5. And P, the probability is constant. It is 80%. I know it's constant because it says it's independent there. So our value of N is 5, and our value of P is 0.8. K would represent the number of successes or makes. The good news is that the calculator can do a lot of this heavy lifting and probability calculations for us. We have two things on here that we can use, one of which is Binomial PDF. Okay, and we get to Binomial PDF, the same spot where we see normal CDF, under second and vars. We have, when we go to Binomial PDF, we have N, P, and K that we have to fill in. So we can use Binomial PDF to create our probability distribution. So let me show you how to go about doing that. I'm going to go into Stat and Edit. I'm going to actually create the table here. So if he makes, or if he takes 5 shots, he can either make 0, 1, 2, 3, 4, or 5. So I'm going to put that into L1. And then in L2, I'm going to go to second and vars, and I'm going to go down to Binomial PDF. So I'm going to scroll down, and there's 2 binomial calculations that we have here. We have PDF and CDF, and I'll talk about both of those. But we're going to go to Binomial PDF. I'm going to put 5 as the number of trials, because that's how many trials we have, and 0.8 as a success. I'm not going to fill in anything in the X value here for now, and I'm going to hit paste. And I'm going to hit enter again. And what it's going to do here is it's filled in the probability of each of those things occurring. So for example, this is the probability that he would make 0 out of the 5 shots. 3.2 e to the negative fourth. Keep in mind that's scientific notation, so that's really 0.00032. The probability that he would make 1 out of the 5 shots is 0.0064. 2 out of the 5, 0.05. 3 out of the 5, 0.2048. 4 out of the 5, 0.4096, and all 5, 0.33. Now, obviously, you would expect if he's making 80% that 4 out of 5 would be the most common occurrence, and that is true. But there's still only a 41% chance if he's making 80% of his shots that he would make 4 out of the 5. So binomial probability calculations are extraordinarily useful here. All right? You don't need to have done this in a table under stat edit. If I get out of this, I could have done each one of these individually by going to second and vars, scrolling down to normal PDF, and say I wanted to know, okay, what's the probability that he's going to make exactly 4? So I'd have my trials at 5, my probability at 0.8, the x value of 4, hit paste, and that'll give me the probability that he's going to make exactly 4 of the shots out of 5, which is 0.4096. So if we head back to the notes here, these are the values that I got in my table under stat and edit, okay? And I used Binomial PDF to get there. We have another function on the calculator, which is Binomial CDF. So while Binomial PDF gets you the probability that he's going to make exactly this many, equal to, Binomial CDF gets you the probability of less than or equal to. PDF stands for probability density function. CDF stands for cumulative density function. Hence, you're adding up all of those that are less than or equal to that value. We do not have any function on the calculator for less than, greater than, or less than or equal to. So in those scenarios, we're going to have to manipulate our CDF or our PDF functions. So use the probability to find that Bill makes 3 or fewer shots. So we're finding the probability that X is less than or equal to 3. Now I could just use my table here and add those up, or I can use the CDF command on my calculator. So I'm going to go to second and vars, over to CDF. My trials are 5. My probability is 0.8. And here I'm saying less than or equal to 3, so my X value is 3. Go ahead and hit paste, and it'll get you your answer of 0.26272. It is crucial, just like when you did normal CDF, when you're using binomial PDF or CDF, that you label your N, your P, and your K. You can do this by hand, okay? We have a binomial probability calculation by hand that we can use. This is on the formula sheet. It says the probability that X is equal to K is equal to NK in parentheses, P to the K times 1 minus P to the N minus K. It looks like a bit of a complicated formula, but it is not that complicated in reality. This NK part in the beginning represents the number of combinations, and choose K, okay? You can get that on the calculator by doing math, PRB, and NCR, okay? This is the factorial that formula is actually showing you here. It's not that important that you know or use this formula all that often, but keep in mind you might see a multiple choice question on the AP exam where they're asking you to apply that formula and say which of the following represents the given probability. So you do need to know this formula, and again, it is on the formula sheet. We'll go through several examples using this formula in class. When we're talking about the mean and the standard deviation for a binomial variable, these formulas are also on the formula sheet. So to find the mean for a binomial situation only, you take N times P. To find the standard deviation of a binomial situation, you take the square root of np times 1 minus p. Both of these formulas are on the formula sheet, and they are not something that we need to worry about here, or memorizing, sorry. And this should make sense to you. For example, say you survey 50 people, and the probability that somebody has brown eyes is 60%. And I want to know, okay, on average, how many people should have brown eyes? You're just going to take 60% times your 50, so 0.6 times 50, to get the actual number you would expect to have brown eyes, which in this case here would be 30 people, okay? So there should be some sense in that formula here. When we're dealing with a binomial, just take the sample size n times the probability of success to get the expected number that would fit into that, or the mean number there. As I said, we'll go through this example in class, as well as the one that follows on the next page and the next page. Okay, so we'll go through all of 20 and 21 in class, as well as 22. So all of these will be done in class. We can head now to the top of page 24, where we're talking about a geometric distribution. So we had a binomial distribution where we have a set number of trials, and we're looking for the number of successes that occur in that number of trials. We're going to talk about another distribution here, which is a geometric distribution. So we had bins for binomial, we have bits for geometric. The only difference between a binomial and a geometric situation is this last part in here. In fact, you're going to see several questions that parts of it are binomial probability calculations and then parts of it are geometric. So in this case here, we still have our two outcomes, success versus failure. The probability of success remains constant. The trials are independent. But for a geometric distribution, we're looking about the number of trials until the first success occurs. So instead of saying, okay, I have 20 people, what is the probability that exactly 10 of them have brown eyes or something like that? Now we're saying, okay, what is the probability it'll take 4 people till I find the first person with brown eyes? Or what is the probability it'll take at least 3 people till I find somebody with brown eyes? When you see that question that's asking about the first success occurring, that's your clue that it's going to be a geometric situation. So as I said, a geometric random variable counts the number of trials to reach the first success. So you have to have at least one trial here. So your x can be anywhere from 1 to infinity till you reach that first success. A geometric distribution is defined by the probability of success. So it's defined by that p. So in the board game Monopoly, one way to get out of jail is to roll doubles. Suppose that a player has to stay in jail until he or she rolls doubles. The probability of rolling doubles is 1/6. So explain why this is a geometric situation, because we're in jail until the first success occurs, until we get that first roll of doubles. So success versus failure, rolling doubles or not, probability is the same. It's always going to be 1/6 chance of rolling doubles. Your rolls are independent. The one roll does not impact the next roll. And we're counting the number of rolls until we get the first roll of doubles. Hence, it's a geometric situation. So it's defined by its probability, which is 1/6, and we're counting the number of rolls till we get doubles. Find the probability that it takes exactly 3 rolls to get out of jail, or exactly 4 rolls. So similar to binomial PDF and CDF, we have geometric PDF and CDF. Now we can do this by hand. If I want to know the probability it's going to take exactly 3 rolls, that means I didn't get doubles, and then I got doubles. So it's an and probability sequence. So didn't get doubles, 5/6, times another didn't get doubles, 5/6, and then on the third roll I got doubles, 1/6. So I can just multiply these across and I would get 0.116. Or I can use the calculator and geometric PDF. Because this is exactly equal to exactly 3 rolls, I know it's a PDF calculation. So I would go to second and vars. I'd go to geometric PDF. It's going to ask me the probability, which in this case is 1/6 of rolling doubles. And I'm saying that it's going to take exactly 3 rolls. Hit paste. The probability that's going to take exactly 3 rolls, or that you'll get doubles on your third roll, is 0.116 or 0.1157. Exactly 4 rolls, you would go to the same thing, second and vars, geometric PDF, change it to 4, and you would get 0.096. Okay? Make sure that you label, if you're using geometric PDF, that you label everything in the calculator as well, P and X, and to get your answer. Find the probability that it takes at most 3 rolls. So at most 3 rolls. That means the probability that X is less than or equal to 3. Lucky for us, there is a function of less than or equal to on the calculator. The only 2 we have are equal to and less than or equal to. So I can just go to geometric CDF. Probability is 1/6, X is equal to 3. So the probability that's going to take at most 3 rolls, or 3 or less, would be 0.421. And again, that's on the same thing, second and vars. And you're down at geometric CDF here, and then just plugging in your values of 1/6 and 3 to get your answer. Now, we are going to look at more complicated examples in class where we have to do more than 3 or less than 3 or things like that. We'll talk about how to do those. You can try to think about what you're going to need to do. A little bit more in the way of notes here to finish things off, though. In general, how can you calculate geometric probabilities? This is also on the formula sheet. You put the number of failures you need and you multiply that times your success whenever that's going to occur to get the formula for a geometric probability. In terms of the mean and the standard deviation for a geometric distribution, these are also on the formula sheet. So your mean for a geometric is 1/p, and your standard deviation for a geometric distribution is is the square root of 1 minus p/p. I want to show you on the formula sheet where these things are located. So on your first page of your formula sheet, notice that it says, okay, for a probability distribution, here's the formula for the mean and the standard deviation that we saw earlier in this chapter. And in here it says, okay, if it's a binomial distribution, here's your binomial distribution formula, as well as the mean and the standard deviation for a binomial. Here's the geometric distribution formula, as well as the mean and the standard deviation for a geometric distribution. What you're going to find the most challenging thing in this section, and this is one of the topics where students struggle the most with, is determining whether it's binomial, geometric, and knowing when to use CDF or whether to manipulate CDF into some other thing in order to calculate the probability. It might seem straightforward, but you're going to see lots of examples in class. I'll see you then.